Okay, I've been listening to the audio in these. I'm sounding kind of nasal to me, so I apologize to that. For that. I apologize to you for that. That's what I meant. Okay, so we have a problem 3. We have this capacitor, which is charged by a 165 volt battery, and then later on it's disconnected and connected to a second capacitor. And then they give us what the potential difference across them is afterwards, and they want to know what the capacitor or the capacitance of the second one is. So let's start with this first sentence here, where you have the capacitor C1, which is charged by the 165 volt battery. Okay, which is pretty impressive battery, I guess. Okay, so anyway, what you have there is you have a battery, and this guy is going to be like that, and that's connected to a capacitor, which is C1. Okay, and the voltage change across, the battery's voltage is 165 volts. So we're going to call this 160. Actually, what I'm going to do, I'm going to keep this symbolic for a moment. So I'm going to call this V1. So the voltage of the battery is V1. Battery voltage is V1. Okay. And then our capacitor C1 here is charged up. And what happens is you get some charge on this guy, of course. You get positive charge on the one plate, so that's going to be a plus Q. And this is going to be a negative Q on the other plate. Positive charge goes on the plate, that's positive voltage. Okay, so we want to find out what Q is. That's not hard, right? We just trot out our capacitor equation. Q equals CV. Or, you know what? I hate changing notation in the middle, but what I'm going to do is I'm going to turn this into VA. So battery voltage A is VA, and there's a reason for that. Okay, so anyway, what we do is we find charge here is going to be just the capacitance on 1, right? The capacitance of 1 times that voltage applied to it. So there you go. Okay, that's the charge that it picks up. Now this is important because, and maybe I should have laid this out beforehand where I was going with this, but this is important because after capacitor 1 is disconnected from the battery and attached to capacitor 2, that's how much charge there is in the new circuit. So capacitor 1, you can imagine this here, capacitor 1 gets disconnected. So there's capacitor 1 all by its lonesome, and it's going to still have charge plus Q on it and minus Q on the other side. Nothing's going to happen there because there's nothing else, nowhere else for the charge to go until you hook it up to capacitor 2. So this is capacitor 2 here, capacitor 1, and you hook them up end to end on both sides. And then what happens is the charge splits up. So some of this positive charge that was on the top side of capacitor 1 up here is going to move over here, and a corresponding amount of the negative charge is going to move over here. So what you're going to have is you're going to have negative Q1 over here and negative Q2, and this is going to be positive Q2, positive Q1, and what you're going to have is Q1 plus Q2, so like these charges up here total are going to be the same as this. Okay? So once you've done that, it's not terribly hard to solve the problem. You take the capacitor equation and apply it to number 1 here. Well, actually, the one thing we do need to remember is that we know now that the voltage across capacitor 1, so let me draw this here, is 18 volts. I'm going to call that VB. VB equals 18 volts. Okay? And so, incidentally, that's also, whoops, hang on, this is Q1 here. Sorry about that. Q1, there we go, not Q2. Okay, so VB is 18 volts, and we know that's the voltage across capacitor 1 because we're told that, but interestingly, it's also the voltage across capacitor 2 because these wires have no voltage change in them within a wire, assuming we have an ideal wire, which we pretend we do in this class. So this gets very easy then because you can apply the same voltage to both capacitors using Q equals CV. So our equation we're using is Q equals CV, And now for capacitor 1, Q1 here, Q1 equals C1 times VB. Q2 over here is C2 times VB. Okay, and then it's very easy because you can take this equation here, this guy, and plug in this, and this. Well, this actually, for the original charge. So what you're doing is you're saying on the left side we have where the charge is after this operation is done. So in this situation is over here on the left side of this equation. And then the earlier charge here is this equation. Okay? So, and we know it's the same amount of charge, so that's easy, right? So C1 VB plus C2 VB, that's Q1 and Q2, equals Q, our original Q, which was C1 VA. C1 VA. So that may be a little bit convoluted, but what you're going to get is you're going to get, and we're trying to find, if you'll recall, we're trying to find C2. That was the whole point of this thing, was to find C2. Okay? So, now what we want to do is we want to isolate C2. So the first thing to do is go C2 VB equals, and then you take this guy, move him more to the right. So you go C1 VA, which is on the right before, minus C1 VB equals, and that's going to equal C1 times VA minus VB. Okay? And so now, I mean, it's pretty easy at this point. The real thing we can get to for an answer, let me just grab a little more space there, is C2 should equal C1 times VA minus VB over VB. And so what did we get? We got C2 was, well, let's see. So, yeah, let's just do this up. So C2 should equal, C1 was, I think, what was it, 7.5 microfarads? Yep. Okay. So C2 is 7.5 microfarads, that's C1 there, times VA minus VB, and as I recall, VA was 165, right, it's battery voltage, and VB was 18, so 165 minus 18, 165 minus 18, 145, 147 volts, okay, 147 volts, that's VA minus VB, and then VB is just 18 volts, and so that gets us C2 equals, hang on, calculator. Okay, let's hope I know how to use this thing. I always hate these calculators. 18 times 7.5. Okay, 61.25. And you'll notice, of course, that we had, you know, volts and volts here. So we want to look at units just to be sure our units are going well. Cancel. And so then we just get the microfarads. Or, yeah, microfarads. And I forgot my... Okay, 61.25. So C2 should be 61.25 microfarads. And I'll circle that in sky blue to show how happy I am about that. Okay.